Okay, in this video, we're going to focus on the distribution of sample means, but we're going to do so when the population happens to be normal. All right, so this is going to be a population is normal. The reason that's important to distinguish is because if the population is normal, I can use the normal distribution or the normal percentages regardless of the sample size. Regardless of the sample size, I'm going to be able to use the normal distributions, even if the sample size is 1. If it's not normal, then I need a sample size of 30 or larger. Okay, so suppose the outstanding credit card balances for young couples are normally distributed with a mean of 650 and a standard deviation of 120. What is the probability that an individual has a credit card balance in excess of $700? Well, basically, because I know the underlying distribution is normal, I'm going to go ahead and set up my picture. My picture looks something like this. Mean is 650. Standard deviation is 120. Credit card balance in excess of 700. Well, this is 700, and we're looking for these. That's our probabilities that we're looking for. All right. So 700 minus 650 divided by 120 gives me this z-score. The probability of that is 0.3385. And there's a couple different ways to do that. Please remember you have to give the z-score. So second var's normal CDF. My lower bound happened to be 700. My upper bound, 99999. My mean was 650. And my standard deviation was 120. And that gives me 0.3385. Of course, I could have also done with the z-score. With the z-score, my lower bound would have been 0.4166. My upper bound, infinity. My mean is 0. My standard deviation is 1, because all z-scores have a mean of 0, standard deviation of 1. Okay, now, with distribution of means, regardless of the sample size, I can divide by the square root of 20. So now, because it's asking for the mean outstanding credit card balance, I know I'm not working with an individual. So I have 20 couples and I'm working with the mean. So this is my formula. And when I plug in, it's going to look something like this: 700 minus 650. And then we have our standard deviation of the population of 120 divided by the square root of 20. Well, this is actually the same picture. The difference is the standard deviation is now divided by the square root of 20. So consequently, it's really going to get a little bit taller than what we initially had. It's going to be less spread out, although the area is greater than 1. I mean, the area will always be 1 regardless of the sample size. So in this case, I can go about doing this a couple different ways, but probably the easiest thing to do would be go to stat test z-test. So if I go to stat test, stat, arrow over to test, and drop down to z-test, my mean happens to be 700. My standard deviation is 120. My x bar, I did that wrong, excuse me. My mean was 650. I'm sorry. My mean was 650. My standard deviation of the population was 120. My sample size was 20. And my x bar was 700, and my sample size was 20. And we wanted to know probability of the mean exceeds 700, so greater than 700. So I make sure I have a greater than symbol. The symbols need to match. And now it's like, wow, 3%. So we went from 33.85% to 3%. Now, one thing I want to point out, if the population had been skewed or if the population had not been normal, I could not have done that problem because the sample size was less than 30. All right, and the central limit theorem would not have applied. But because the underlying population was normal, I could still use the normal distribution. The central limit theorem says it becomes normal if the population, if the sample size is large enough. Well, in this case, it was already normal, so we were good to go. Part C. In a simple random sample of 80 couples, what's the probability the mean outstanding credit card balance exceeds 700? Now, this one, because I'm already, and by the way, they're asking for the mean, and we have to be careful to make sure they're asking for the mean, because the distribution of the sample means only applies to the means. I could still do this even if the underlying population were not normal, because my sample size is large enough. So once again, we're taking the same initial drawing that we had, but instead of drawing by the square root of 20, it's now the square root of 80, and we're expecting something substantially narrower. Once again, I would set it up. I have to show my z-score, and probably, again, the easiest way to go about this would be a stat test z-test. Stat test z-test, 650, 120, and I'm changing my sample size to 80. Still a greater than symbol. And it calculated everything for me. I have a z of 3.76, and I end up getting 0.00097. And I'm going to tell you my rule of thumb is if you end up with 4 zeros, you can just put the approximately 0. All right. Here I showed it, but really we only need that. And notice I have to the -5, which means I have 4 zeros out in front. So if the population had been skewed, I still could have done this problem because central limit theorem applied. So in this case, we were working with an underlying normal distribution. So we could definitely do the distribution of means regardless of the sample size. So central limit theorem basically says, once again, if the underlying population is not normal, then we can say that it approximates the normal if we're talking about the means and our sample size is 30 or larger. Regardless as to whether or not if it's already normal, we can definitely use the distribution of means, okay? So if the underlying population is normal, we can use the distribution of means always. Thank you.